Now, as proposed, I'm going to introduce a problem with the model, is that if we expand things, we alter measures of intervals of time. And this is illustrated here. We have a pendulum. And if the pendulum were to be expanded, it would define a longer period of time. So that would mean that not only are measures of distance changing, but measures of time are changing. And which presents kind of a problem, which I'll illustrate over here. One of the things proposed by the model, and it also is a requirement of special and general relativity, is that intervals of time are invariant. What I mean by this, let's say we establish a matrix and the intersections here describe locations of point in time. And let's say from here to here is represented to be roughly 3 times 10 to the 8th meters, which allows that it would take this photon moving at the speed of light 1 second to go from here to here. So each point in this matrix of space is separated by a distance interval and a temporal interval, 3 times 10 to the 8th meters and 1 second in time. Now, if this matrix were to be expanded, so all the relative measures of distance have expanded, the temporal relationship would also have to be maintained in order for what's called invariant, that the local measures of distance and time are keeping their proportional measure. If it took 1 second to go from here to here, it would also have to take 1 second to go from here to here. You know, the separation between the relative measures of distance and the relative measures of time would have to keep their same proportional relationship over time. And as seen over there, that this kind of is a stringent requirement of the model, that relative measures of distance and relative measures of time have to be maintained or invariant in this proposed expansion. Now, to explain this and how this resolves out is done by what's considered what I call the kinematic cost of expansion. And I mentioned earlier, here we have a balloon, and in this balloon are molecules that are moving around. And when the balloon expands, there is a corresponding drop in the kinematic velocity of the molecules within the balloon. So expansion comes at a cost. Well, what kind of kinematic cost would occur in an expanding space-time field for objects in motion? Well, the first thing that is part of it is that the kinematic cost would somewhat be proportional to the initial velocity of the object. Let's say here we have a region of space-time, and these tiny little dots represent an incremental expansion of a void within the existing structure of space. And here we can see at this velocity, only so many voids will be encountered, and if it's twice as fast, it will encounter twice as many voids. So as the moving object encounters these voids, there's a loss of kinetic energy. So it would be proportional, the loss of velocity would be proportional to the velocity. Now, and this was mentioned as one of the premises of the model, is that the relationship that defines how velocity changes for distance measures associated with the object also defines the behavior of matter within this expanding space-time. So what that means is that the velocity at some point of an object in the past, and here it is in the present, is going to be equal to the absolute ratio of time to the 1/3 power, or if I inverted to get the terminology, saying V1 over V2 would have been T1 over T2 to the minus 1/3 power, just to keep the notation standard. But anyways, the same relationships define the expansion of the object also defines the behavior of particles within this expanding space-time field. And similarly, once we have the velocity relationship, if we take the derivative of that relationship, we'll get an accelerative term. Now, this is defining actually a kind of structure, a dynamic structure within space-time, where the accelerative field within the space-time is actually produced from the expansion, and the characteristics of the dimensional characteristics of the matter determines how that is expressed in terms of magnitude, where it's going to be charge or it's going to be gravity. So now, if you adopt this behavior of matter within an expanding space-time field, does it maintain all measures of relative measures of time? Well, before I get into that, I guess here is a graphical prediction. Then what this shows is that at the present time, if we were to go back in time, here's the beginning of time, how distance measures, not only just of the object and velocities of an expanding space-time field, but also the behavior of objects within a space-time field. So if it has a certain velocity, the velocity would vary like this, and we go back in time, it would accelerate. Okay, there would be more and more greater energy. So now let's see how, and also the accelerative field associated would vary in such a proportion as a part of the actual structure of space-time itself. And let's see what this does in terms of our measures of intervals of time.